What is the universe expanding into? The most perplexing question in cosmology. When you hear that the universe is expanding, your first instinct is probably to ask the same question that has puzzled scientists and laypeople alike for nearly a century. Expanding into what? It's a natural question, almost impossible not to ask. After all, everything we experience in our everyday lives expands into something else. A balloon expands into the air around it. A city expands into the surrounding countryside. Even your lungs expand into the space within your chest cavity. The idea that something could expand without expanding into anything seems to violate common sense, to contradict the very nature of expansion itself. Yet this is precisely what cosmologists tell us about the universe. The universe is expanding, they say, but it's not expanding into anything. There is no outside, no surrounding space, no container or void that the universe is filling up. The expansion is intrinsic to space itself. This statement sounds like a riddle or a paradox. How can something expand without having something to expand into? Is this just physicists playing word games? Or is there a genuine, profound insight here about the nature of reality? The answer, as we'll discover, is that our intuitions about space and expansion are fundamentally flawed. They're based on our experience with objects moving through space, but the expansion of the universe is not about objects moving through space. It's about space itself changing, stretching, growing. To understand what the universe is expanding into, we need to fundamentally rethink what we mean by space, what we mean by expansion, and even what we mean by the universe itself. This question sits at the intersection of cosmology, general relativity, and philosophy. It forces us to confront the limits of our language and our imagination. The concepts involved are genuinely difficult, not because they require advanced mathematics, though they do, but because they require us to think in ways that don't come naturally to minds that evolved to navigate a world of 3 spatial dimensions at human scales. We need to abandon our preconceptions about space as a fixed stage on which events unfold, and instead see it as a dynamic, evolving entity in its own right. We need to understand that the universe is not a thing in space, but rather that space is part of the universe. The journey to answer this question will take us through the history of cosmology, from Einstein's first cosmological models to the discovery of the expansion itself by Edwin Hubble, from the Big Bang Theory to modern concepts of cosmic inflation and the multiverse. We'll explore what physicists mean when they talk about the fabric of space-time, how general relativity describes gravity not as a force, but as the curvature of space, and why this curvature means that space can expand without needing anything to expand into. We'll confront analogies like the balloon and the raisin bread, useful starting points that nonetheless fail to fully capture the strangeness of cosmic expansion. And we'll grapple with the philosophical implications of a universe that is, in some sense, everything that exists, leaving no room for an outside. Before we dive into the deep end, let's start with the basics. Drop a comment below telling me where you're watching from and what time it is in your part of the world. And as we embark on this mind-bending journey through space, time, and the very nature of reality, make sure you're subscribed and hit that notification bell so you don't miss future videos exploring the biggest questions in science. Now, let's tackle one of the most profound questions humans have ever asked. What is the universe expanding into? The discovery of cosmic expansion. To understand what the universe is expanding into, we first need to understand that the universe is expanding at all. And this realization is surprisingly recent in human history. For most of recorded time, humans assumed that the universe was essentially static and unchanging on cosmic scales. Stars might be born and die, planets might orbit, but the overall structure and size of the cosmos was thought to be fixed and eternal. This view prevailed even as astronomy became a rigorous science in the centuries following the scientific revolution. Newton's laws of motion and gravity described a universe that could be dynamic in its details, with objects moving and interacting. But the framework itself, the stage on which these motions occurred, was assumed to be unchanging. This changed in the early 20th century with the development of general relativity by Albert Einstein. Published in 1915, general relativity revolutionized our understanding of gravity, space, and time. Einstein showed that gravity is not a force transmitted instantaneously across space, as Newton had thought, but rather a consequence of the curvature of space-time itself. Massive objects, like stars and planets, warp the fabric of space-time around them, and other objects move along the curved paths created by this warping. It's often said that matter tells space-time how to curve, and space-time tells matter how to move. This was a radical departure from the Newtonian picture, and it had profound implications for cosmology, the study of the universe as a whole. When Einstein first applied his equations to the universe at large, he made a startling discovery. The equations of general relativity did not naturally produce a static universe. Instead, they predicted that the universe should either be expanding or contracting. This troubled Einstein deeply. Like almost everyone else at the time, he believed the universe was static and eternal. To force his equations to produce a static solution, he introduced an additional term called the cosmological constant, a kind of repulsive force that could exactly balance the attractive force of gravity on cosmic scales. This allowed him to construct a model of a static universe that was stable and unchanging. The cosmological constant was, in Einstein's own later assessment, one of the biggest blunders of his career, though, as we'll see, the concept has made a comeback in modern cosmology in the form of dark energy. While Einstein was trying to keep the universe static, observational astronomers were making discoveries that would overturn the static paradigm. In the 1,910 seconds and 1,920 seconds, Vesto Slipher measured the spectra of spiral nebulae, those fuzzy patches of light visible through telescopes that were thought by some to be objects within the Milky Way and by others to be distant galaxies. Slipher found that most of these nebulae exhibited redshifts, meaning their light was shifted toward longer, redder wavelengths. According to the Doppler effect, this indicated that the nebulae were moving away from us. This was a curious finding, but its full significance was not immediately clear. The breakthrough came in the late 1,920 seconds, when Edwin Hubble, working at the Mount Wilson Observatory with the largest telescope in the world at the time, combined Slipher's velocity measurements with his own distance measurements. Hubble used Cepheid variable stars, whose pulsation periods are related to their intrinsic brightness, to determine the distances to several spiral nebulae. He found that these objects were far beyond the Milky Way, confirming that they were indeed separate galaxies. More importantly, he discovered a relationship between the distance to a galaxy and its velocity of recession. The farther away a galaxy was, the faster it was moving away from us. This relationship, now known as Hubble's law, was announced in 1929 and provided the first clear evidence that the universe is expanding. Hubble's discovery was revolutionary. It meant that the universe was not static but dynamic, growing larger over time. Galaxies were not simply moving through a fixed space. Rather, the space between them was stretching, carrying them apart. This expansion was not centered on any particular location. Every galaxy saw every other galaxy moving away, with more distant galaxies receding faster. This observation is consistent with a uniform expansion of space itself, where distances between all points increase proportionally over time. The implications were profound and immediate. If the universe is expanding, then it must have been smaller in the past. Extrapolating backward in time, the universe must have been denser and hotter, eventually reaching a state of extreme density and temperature. This realization laid the groundwork for the Big Bang Theory, the idea that the universe began in a hot, dense state and has been expanding and cooling ever since. The Belgian priest and physicist Georges Lemaitre, working independently, had actually proposed a similar idea even before Hubble's observational confirmation, suggesting that the universe began as a primeval atom that exploded and expanded. The term Big Bang itself was coined later, in the 1940 seconds, by Fred Hoyle, who was actually a critic of the theory and preferred a steady-state model of the universe. The discovery of cosmic expansion immediately raised the question we're exploring. Expanding into what? If the universe is getting bigger, what is it getting bigger within? Is there a pre-existing space or void that the universe is filling? These questions troubled many scientists and continue to perplex people today. The answer, which we'll explore in detail, lies in understanding that the expansion is not of the universe into something else, but of space itself. The universe is not like a balloon expanding into the air around it. It's more like the balloon's surface, but without the air inside or outside, just the surface itself, stretching and growing. The nature of space-time. To truly grasp what the universe is expanding into, or rather, what it means for the universe to expand without expanding into anything, we need to understand the nature of space-time as described by general relativity. This is where things get genuinely strange, because space-time is not at all like the simple, fixed, three-dimensional grid that we imagine when we think of space in everyday terms. In classical physics, space was thought of as a stage, a fixed background on which the drama of the universe unfolds. Objects move through space, interact with each other, but space itself is passive and unchanging. It's just there, providing a framework for measuring distances and directions. Time, in this view, is separate from space, a universal clock that ticks at the same rate everywhere, independent of motion or gravity. This Newtonian conception of absolute space and absolute time was intuitive and worked remarkably well for describing the motion of everyday objects and even the orbits of planets. Einstein's special relativity, published in 1905, began to undermine this picture. Special relativity showed that space and time are not separate and absolute, but are interwoven into a single four-dimensional entity called space-time. The separation between space and time depends on the observer's state of motion. What one observer considers simultaneous, another observer moving relative to the first does not. Distances contract and time dilates depending on relative velocity. These effects are small at everyday speeds, but become significant as velocities approach the speed of light. Special relativity introduced the idea that space and time are not fixed, but depend on the observer's frame of reference. General relativity, Einstein's 1915 theory of gravity, took this further. It showed that space-time is not just a passive stage, but a dynamic entity that can bend, stretch, and curve in response to the presence of matter and energy. Massive objects create curvature in space-time, and this curvature is what we perceive as gravity. A planet orbits a star not because the star is pulling on it through some mysterious action at a distance, but because the star's mass warps the space-time around it, and the planet moves along the straightest possible path, called a geodesic, through this curved space-time. In a real sense, the planet is not deviating from a straight line. Rather, the definition of a straight line has changed because of the curvature. This concept of space-time curvature is central to understanding cosmic expansion. If space-time can curve, it can also stretch and expand. The expansion of the universe is not about galaxies moving through a fixed space, flying apart from some central explosion point. Instead, it's about the space itself between galaxies, increasing over time. Imagine a rubber sheet with dots marked on it. If you stretch the sheet, the dots move apart, but not because they're sliding across the sheet. The sheet itself is expanding, carrying the dots with it. This is analogous to what's happening with the universe, though the analogy is imperfect because the sheet is two-dimensional and embedded in three-dimensional space, whereas the universe's expansion happens in three-dimensional space, not embedded in any higher dimensional space that we know of. The mathematics of general relativity describes space-time using a metric, a mathematical object that encodes information about distances and angles in space-time. In flat, unchanging space, the metric is simple and constant, but in a curved or expanding space-time, the metric varies from point to point or changes with time. For an expanding universe, the metric includes a scale factor that increases over time, representing the stretching of space. This scale factor is not arbitrary. It's determined by the matter and energy content of the universe through Einstein's field equations, the core mathematical structure of general relativity. One crucial aspect of this description is that the expansion is intrinsic to space-time itself. It's not about space expanding within some larger container or arena. There is no external reference frame, no outside observer measuring the expansion from the outside. The expansion is defined entirely within the universe, in terms of how distances between points in space change over time as measured by observers within the universe. This is a subtle but essential point. When we ask what the universe is expanding into, we're implicitly assuming an external perspective, a vantage point outside the universe from which we could watch it grow. But general relativity tells us there is no such external perspective, at least not one that's accessible or necessary for describing the universe. Space-time, in general relativity, is not a thing that exists independently of the matter and energy within it. Instead, space-time and matter are deeply interconnected. Matter tells space-time how to curve, and space-time tells matter how to move. This reciprocal relationship means that the geometry of space-time and the distribution of matter and energy evolve together. In the context of the expanding universe, the expansion of space-time is driven by the energy density of the universe. In the early universe, when densities were extremely high, the expansion rate was very rapid. As the universe expanded and densities decreased, the expansion rate slowed, though as we'll discuss later, recent observations indicate that the expansion is currently accelerating due to dark energy. The Big Bang and the origin of expansion. Understanding cosmic expansion naturally leads to questions about the beginning. If the universe is expanding now, and has been expanding for billions of years, then going backward in time, the universe must have been smaller and denser in the past. Extrapolating all the way back, we arrive at the concept of the Big Bang, the idea that the universe began from an extremely hot, dense state, approximately 13.8 billion years ago. The Big Bang is often misunderstood as an explosion in space, a blast that sent matter flying outward from some central point. But this is not what the Big Bang theory describes. The Big Bang was not an explosion in space. It was an expansion of space itself. At the moment often referred to as the Big Bang, space-time itself came into existence, or at least entered a regime that we can describe with our current physics. There was no pre-existing space for the universe to explode into. There was no before the Big Bang in the conventional sense, because time itself began with the Big Bang, or at least our current understanding of time breaks down at that point. This is deeply counterintuitive. We're used to thinking of every event as having a cause that preceded it in time, but if time itself began with the Big Bang, the question of what came before becomes meaningless, or at least beyond the reach of our current theories. The evidence for the Big Bang comes from multiple independent sources. The most direct evidence is the cosmic microwave background, or CMB, a faint glow of radiation that fills the entire universe. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, the CMB is the afterglow of the Big Bang, radiation that was emitted when the universe was about 380,000 years old and has been travelling through space ever since, cooling and redshifting as the universe expands. The temperature of this radiation is now about 2.7 Kelvin, just a few degrees above absolute zero, but it was much hotter in the past. The existence and properties of the CMB are precisely predicted by the Big Bang theory and provide strong confirmation of the model. Another line of evidence comes from the observed abundances of light elements like hydrogen, helium, and lithium. The Big Bang theory predicts that in the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear reactions to occur, a specific mixture of these elements was produced. Observations of the oldest stars and gas clouds in the universe match these predictions remarkably well, providing another independent confirmation of the Big Bang. The expansion rate itself, measured through observations of distant galaxies and supernovae, also supports the Big Bang model. By measuring how fast galaxies at different distances are receding, astronomers can reconstruct the expansion history of the universe and determine its age. Current measurements indicate that the universe is about 13.8 billion years old, consistent with other lines of evidence, such as the ages of the oldest stars. But the Big Bang raises profound questions. What caused it? Why did the universe begin in such a hot, dense state? And critically for our discussion, if the universe began expanding at the Big Bang, what was it expanding into? The answer, according to standard cosmology, is nothing. The Big Bang was not an explosion into pre-existing space, but the beginning of space itself. Before the Big Bang, or more accurately, at times earlier than the Big Bang, the concepts of space and time as we understand them do not apply. There was no outside for the universe to expand into, because the universe, by definition, includes all of space. This is where language and intuition fail us. We naturally think of the universe as a thing, an object with boundaries, and we imagine it expanding like a balloon or a bubble. But the universe is not a thing within space. It is space, along with all the matter and energy it contains. The expansion is not of a bounded object within a larger space, but of space itself, uniformly at every point. Every location in the universe can be considered the center of the expansion in the sense that observers at any location see galaxies receding in all directions, with more distant galaxies receding faster. There is no edge and no center, or alternatively, every point is the center. The balloon analogy and its limitations. One of the most common ways that cosmologists try to explain cosmic expansion to the public is through the balloon analogy. This analogy is helpful but also potentially misleading, and it's worth exploring both its usefulness and its limitations in detail. The analogy goes like this. Imagine the surface of a balloon with dots drawn on it. As you inflate the balloon, the surface expands and the dots move apart from each other. Crucially, no dot is at the center of the expansion. Each dot sees all the other dots moving away, with dots that are farther away moving faster. This mimics the behavior of galaxies in our expanding universe. The surface of the balloon represents space, and the dots represent galaxies. The expansion of the balloon's surface is analogous to the expansion of space in the universe. This analogy has several strengths. First, it helps visualize how expansion can occur without having a center. On the two-dimensional surface of the balloon, there's no special point that is the center of the expansion. Every point on the surface is equivalent, just as every point in the universe is equivalent in the cosmological principle. The idea that the universe looks roughly the same in all directions and from all locations on large scales. Second, it illustrates how space itself is expanding, not just objects moving through space. The dots on the balloon are not sliding across the surface. The surface itself is stretching, carrying the dots with it. Similarly, galaxies in the universe are not flying through space. Space itself is expanding between them. Third, the balloon analogy helps explain Hubble's law, the observation that more distant galaxies are receding faster. On the balloon, dots that are farther apart move away from each other faster as the balloon inflates, even though the rate of expansion of the surface is uniform everywhere. This is because there's more expanding surface between widely separated dots than between nearby dots. The same principle applies to the universe. The recession velocity of a galaxy is proportional to its distance, not because galaxies farther away are moving faster through space, but because there's more space between us and them, and all of that space is expanding. However, the balloon analogy has significant limitations that can lead to misconceptions if taken too literally. The most glaring limitation is that the balloon's surface is two-dimensional, while our universe has three spatial dimensions. We can imagine the two-dimensional surface of a balloon embedded in three-dimensional space, with the balloon expanding into the third dimension. This naturally leads to the question: if the universe is three-dimensional, is it embedded in a higher dimensional space into which it is expanding? The answer, according to general relativity, is no, or at least such an embedding is not necessary. The universe can expand within its own three-dimensional space without requiring a higher dimensional space to expand into. Another limitation is that the balloon has an inside and an outside. We can picture air inside the balloon and the room around the balloon, both of which are outside the two-dimensional surface. This reinforces the intuition that the universe must be expanding into something, some external space or void. But in the actual universe, there is no inside or outside. The universe is not a surface or a volume within a larger space. It is all of space. The analogy breaks down because we're using a lower dimensional example, the balloon's surface, to represent a higher dimensional reality, the universe's three-dimensional space. A related issue is that the balloon analogy suggests that the universe is finite, like the finite surface area of a balloon. And indeed, one possibility in cosmology is that the universe is spatially finite but unbounded, meaning it has a finite volume but no edge, much like the surface of a balloon has finite area but no edge. You could travel in any direction on the balloon's surface and never reach a boundary. You'd eventually come back to where you started. This is called a closed universe, one with positive curvature. However, observations suggest that our universe is either flat or very close to flat, meaning it could be infinite in extent. In a flat universe, space goes on forever, in all directions, like an infinite plane. The balloon analogy doesn't capture this possibility well, since balloons are finite. Another subtlety is the role of the center of the balloon. In the three-dimensional space that contains the balloon, there is a center point inside the balloon. But on the two-dimensional surface itself, there is no center. Any ant crawling on the surface would not be able to identify a central point on the surface. Similarly, in our three-dimensional universe, there is no center of the expansion within the three-dimensional space. However, people often confuse the center inside the balloon, which is not part of the two-dimensional surface, with the idea of a center of expansion. This confusion can lead to questions like, where did the Big Bang happen? The answer is that it happened everywhere. Every point in space was part of the initial singularity, and the expansion began everywhere at once. Despite these limitations, the balloon analogy remains a useful pedagogical tool because it provides a concrete, visualizable example of expansion without a center, and it helps people understand that space itself is what's expanding. The key is to remember that it's an analogy, not a perfect representation, and to be aware of where it breaks down. When thinking about what the universe is expanding into, the balloon analogy should remind us that expansion can be an intrinsic property of space, not requiring an external arena, even though the analogy itself uses an external space for convenience. Finite versus infinite universes. One of the deepest questions in cosmology, closely related to the question of what the universe is expanding into, is whether the universe is finite or infinite in size. This question touches on the geometry of space, the topology of the universe, and the ultimate fate of cosmic expansion. General relativity allows for different possible geometries of space, depending on the total density of matter and energy in the universe. There are three main possibilities, often called flat, open, and closed universes, corresponding to zero, negative, and positive curvature, respectively. A flat universe has Euclidean geometry. Parallel lines remain parallel. The angles in a triangle add up to 180 degrees, and the ratio of a circle's circumference to its diameter is pi. In a flat universe, space extends infinitely in all directions. If you could somehow travel in a straight line forever, you would never come back to your starting point, nor would you reach an edge. A flat universe is infinite in extent and has infinite volume, though it can be finite in age. The observable universe, the region from which light has had time to reach us since the Big Bang, is finite, but the entire universe extends beyond what we can see, possibly forever. An open universe has negative curvature, like the surface of a saddle. In such a geometry, parallel lines diverge, and the angles in a triangle add up to less than 180 degrees. Like a flat universe, an open universe is infinite in extent. The negative curvature affects the large-scale structure and the rate of expansion, but it does not introduce edges or boundaries. An open universe is also infinite and unbounded. A closed universe has positive curvature, like the surface of a sphere. In this geometry, parallel lines eventually converge, and the angles in a triangle add up to more than 180 degrees. A closed universe is finite in volume, but has no boundaries or edges, much like the surface of a sphere is finite in area, but has no boundary. If you traveled in a straight line in a closed universe, you would eventually return to your starting point, having circled the entire universe. This is analogous to traveling around the Earth's surface and coming back to where you started. Which type of universe do we live in? The answer comes from observations of the geometry of space, primarily through measurements of the cosmic microwave background. The CMB contains tiny temperature fluctuations, and the angular size of these fluctuations depends on the curvature of space. If space is flat, the fluctuations appear at a certain angular scale. If space is curved, the fluctuations would appear larger or smaller. Precise measurements by satellites like WMAP and Planck have found that the universe is flat, or at least very close to flat, to within about 0.4%. This suggests that the universe is either exactly flat or has such slight curvature that it is indistinguishable from flat over the observable universe. If the universe is flat, then it is most likely infinite in extent. An infinite universe has profound implications. It means that space goes on forever, with no edge or boundary. There is always more universe beyond any horizon we can observe. This raises questions about whether there are regions of the universe beyond our observable horizon that are fundamentally different from ours, with different physical conditions or even different laws of physics. Though the cosmological principle suggests that the universe is homogeneous and isotropic on large scales, looking the same everywhere, an infinite universe also complicates the question of what the universe is expanding into. If the universe is already infinite and it's expanding, does it become more infinite? This sounds nonsensical, but mathematically it makes sense. Infinity is not a number, but a concept, and different infinities can be related by scaling. When we say an infinite universe is expanding, we mean that the distances between any 2 points in space are increasing over time. The scale factor of the universe is growing, so distances that were a certain size in the past are larger now and will be even larger in the future. The universe was infinite in the past, is infinite now, and will be infinite in the future. But the size of structures within it, the distances between galaxies, for example, changes over time. If the universe is closed, then it is finite in volume, though still without boundaries. This scenario is sometimes easier to conceptualize because we can imagine a finite, bounded entity like a sphere. But even in a closed universe, the question of what it's expanding into remains. The universe is not expanding into a higher dimensional space in the way the balloon's surface expands into three-dimensional space. The expansion is intrinsic to the three-dimensional space of the universe itself. The volume of the universe increases over time, but this increase happens within the universe's own geometry, not within some external space. The distinction between finite and infinite also affects the ultimate fate of the universe. In a flat or open universe, expansion can continue forever, with the universe growing ever larger and cooler, eventually reaching a state of maximum entropy called heat death. In a closed universe, the expansion might eventually halt and reverse, leading to a big crunch where the universe collapses back to a singularity. However, recent observations of accelerating expansion driven by dark energy suggest that even if the universe is closed, it may expand forever, with dark energy preventing a recollapse. The observable universe versus the entire universe. A critical distinction that often gets overlooked in discussions of cosmic expansion is the difference between the observable universe and the entire universe. This distinction is essential for understanding what the universe is expanding into and for addressing common misconceptions about the nature of the cosmos. The observable universe is the region of space from which light has had time to reach us since the Big Bang. Because the universe has a finite age, about 13.8 billion years, and because light travels at a finite speed, there is a limit to how far we can see. Light from objects beyond a certain distance simply hasn't had enough time to reach us yet. This defines a spherical region centered on Earth, called the observable universe, with a radius of about 46 billion light-years in co-moving coordinates, accounting for the expansion of space during the time the light has been traveling. The entire universe, on the other hand, is everything that exists, both the parts we can see and the parts we cannot. If the universe is infinite, as suggested by the flatness measurements, then the entire universe is infinitely larger than the observable universe. There is no edge to the entire universe, no boundary beyond which there is nothing. The observable universe is simply the portion that is accessible to our observations, limited by the finite age of the universe and the finite speed of light. This distinction is crucial for understanding cosmic expansion. When we observe distant galaxies receding from us, we're observing objects within the observable universe. The expansion we measure is the expansion of space between us and those galaxies. But the expansion is happening everywhere in the universe, not just in the observable part. Space is stretching between all galaxies, in all regions, even those far beyond our observational horizon. One implication of this is that there are galaxies beyond our observable universe that we will never be able to see, not because they're not there, but because the light from them will never reach us. In fact, because the expansion is accelerating, driven by dark energy, there are galaxies that we can see now, but whose future light will never reach us. The observable universe, in a sense, is shrinking in terms of the number of galaxies we can potentially observe, even as the physical distances to those galaxies continue to increase. Another implication is that when we ask what the universe is expanding into, we need to specify whether we mean the observable universe or the entire universe. The observable universe is expanding in the sense that its radius is increasing as light from more distant regions reaches us. This is an expansion of our observational horizon, not necessarily an expansion of space itself. The entire universe, on the other hand, is expanding in the sense that distances between all points in space are increasing over time. If the universe is infinite, it was infinite in the past, is infinite now, and will be infinite in the future, but the scale of structures within it changes. This also clarifies a common source of confusion: the idea that the Big Bang was an explosion from a single point. If the entire universe is infinite, then it was always infinite, even at the moment of the Big Bang. The Big Bang was not an explosion at a point, it was a rapid expansion of all of space. Every point in space was part of the initial singularity, and the expansion began everywhere at once. In an infinite universe, there is no center of the Big Bang because every point can be considered the center, or alternatively, there is no center at all. The observable universe provides a kind of cosmic perspective, a reminder that what we can see is just a tiny fraction of what exists. It's humbling to realize that the vast expanse of galaxies visible through our telescopes, numbering in the hundreds of billions, represents only a small portion of the entire universe, possibly an infinitesimal portion if the universe is truly infinite. Yet even this small portion is more than enough to study and understand the fundamental laws of physics and the large-scale structure of the cosmos, cosmic inflation, and the expansion of space. One of the most important developments in cosmology in recent decades has been the theory of cosmic inflation, which provides a mechanism for the early rapid expansion of the universe and helps explain several puzzles about the large-scale structure of the cosmos. Inflation also has implications for our question about what the universe is expanding into. Inflation is the idea that in the first fraction of a second after the Big Bang, the universe underwent an incredibly rapid exponential expansion, growing by a factor of at least 10 to the power of 26 inches, a time interval of about 10 to the power of negative 32 seconds. During this brief period, a region of space much smaller than a proton expanded to become larger than the observable universe today. This inflationary expansion was driven by a special kind of energy field called the inflaton field, which temporarily dominated the energy density of the universe and caused space to expand at an accelerating rate. Inflation solves several problems in cosmology. One is the horizon problem. The cosmic microwave background has almost exactly the same temperature in all directions to within about 1 part in 100,000. This uniformity suggests that different regions of the early universe were in thermal equilibrium, meaning they had been in contact and able to exchange energy. But according to standard Big Bang cosmology without inflation, regions on opposite sides of the sky were too far apart to have ever been in contact. Light could not have traveled between them in the time available. Inflation solves this by proposing that all the regions we observe today were much closer together before inflation, close enough to be in thermal equilibrium. Inflation then expanded these regions to enormous distances, preserving their initial uniformity. Another problem is the flatness problem. Observations indicate that the universe is very close to flat, with its total energy density extremely close to the critical density that divides open from closed universes. This flatness requires an extraordinary fine-tuning of the initial conditions of the universe. Any deviation from flatness in the early universe would have been amplified over time, yet we observe the universe to be flat to high precision. Inflation solves this by exponentially expanding space, smoothing out any initial curvature and driving the geometry toward flatness. It's like inflating a balloon to enormous size. The surface becomes so large that any local region appears flat, even though the overall shape might be curved. Inflation also predicts the existence of tiny quantum fluctuations in the inflaton field, which get stretched to macroscopic scales by the expansion. These fluctuations become the seeds for the formation of galaxies and large-scale structure. They leave an imprint on the cosmic microwave background in the form of temperature fluctuations. And the predictions of inflation for the pattern of these fluctuations match observations remarkably well. This is one of the strongest pieces of evidence supporting the inflationary paradigm. In the context of our question about what the universe is expanding into, inflation provides a vivid example of how space itself can expand, and expand rapidly, without requiring an external space to expand into. During inflation, space was expanding faster than the speed of light. This does not violate special relativity, which only prohibits objects from moving through space faster than light. There is no limit on how fast space itself can expand. The inflationary expansion was intrinsic to space, driven by the energy of the inflaton field, and it did not require any pre-existing space or external arena. Inflation also suggests that our observable universe is just a tiny patch of a much larger, possibly infinite, space. If inflation occurred, the entire universe is vastly larger than what we can observe, and there may be other regions of space, far beyond our horizon, where conditions are different. This leads to the concept of the multiverse, which we'll explore shortly. It's worth noting that while inflation is the leading paradigm for the early universe and is supported by strong observational evidence, it is not without its challenges and critics. The exact nature of the inflaton field remains unknown, and there are many different models of inflation with different predictions. Some physicists question whether inflation is truly a well-defined scientific theory, or whether it is too flexible, able to accommodate almost any observation. Despite these debates, inflation has been remarkably successful in explaining the large-scale structure of the universe, and remains a cornerstone of modern cosmology. Dark energy and the accelerating expansion. In 1998, observations of distant supernovae led to one of the most surprising discoveries in the history of cosmology. The expansion of the universe is accelerating. This was completely unexpected. Based on the known forms of matter and energy in the universe, all of which exert attractive gravitational forces, cosmologists expected that the expansion should be slowing down over time. The discovery that the expansion is actually speeding up implied the existence of a new form of energy, dubbed dark energy, which exerts a kind of repulsive gravitational effect, pushing space apart. Dark energy is one of the greatest mysteries in physics. It makes up about 68% of the total energy density of the universe, yet we have no idea what it is. The simplest explanation is that dark energy is a property of space itself, a kind of vacuum energy or cosmological constant, the very term that Einstein introduced and later abandoned. If space has a non-zero energy density that remains constant as the universe expands, this energy would exert a repulsive gravitational effect, causing the expansion to accelerate. This is consistent with observations, but it raises profound questions. Why does space have this energy? Why is its value what it is, rather than something vastly larger or smaller? The discovery of dark energy and the accelerating expansion has important implications for the ultimate fate of the universe. If the acceleration continues, the universe will expand forever, growing ever larger and colder. Galaxies beyond our local group, which are gravitationally bound to us, will recede beyond the cosmic horizon, eventually becoming unobservable. Stars will burn out, black holes will evaporate through Hawking radiation, and the universe will approach a state of maximum entropy, cold and dark, with no structure or activity. This scenario is sometimes called the Big Freeze, or heat death, and it is the most likely fate of the universe, given current observations. Dark energy also affects our understanding of what the universe is expanding into. If dark energy is a property of space itself, then as space expands, more dark energy is created, or more precisely, the total energy of dark energy increases proportionally to the volume of space. This seems to violate the conservation of energy, but in general relativity, energy conservation is more subtle. The energy of matter and radiation decreases as the universe expands, due to redshifting and dilution, but the energy of dark energy increases. The total energy of the universe, including dark energy and the gravitational potential energy associated with the curvature of space-time, can remain constant or even be zero, depending on how you define and account for gravitational energy. The accelerating expansion driven by dark energy means that the universe is not just expanding, but expanding at an ever-increasing rate. The scale factor of the universe, which describes how distances change over time, is growing exponentially. This exponential expansion is similar to what occurred during inflation, though at a much slower rate. In fact, some cosmologists speculate that dark energy and the inflaton field might be related, both representing phases of accelerated expansion driven by the properties of space itself. Understanding dark energy is one of the primary goals of modern cosmology. Numerous experiments and observatories are dedicated to measuring the properties of dark energy with ever greater precision, hoping to determine whether it is truly a cosmological constant or something more exotic that changes over time. The answer will have profound implications for the fate of the universe and for our understanding of fundamental physics, the multiverse, and eternal inflation. The concept of cosmic inflation, particularly in some of its more speculative formulations, leads to the idea of a multiverse, a vast ensemble of universes, each potentially with different properties and physical laws. This idea is both fascinating and controversial, and it has interesting implications for our question about what the universe is expanding into. In some models of inflation, the inflationary phase does not end everywhere at the same time. Instead, inflation ends in some regions, creating bubble universes like ours, while continuing in other regions. This process, called eternal inflation, means that inflation never truly ends globally, but continues forever, constantly spawning new bubble universes. Each bubble universe has its own Big Bang, its own evolution, and potentially its own laws of physics, depending on how fundamental constants and parameters are determined in the transition from the inflationary phase to the post-inflationary phase. In this picture, our observable universe is just one bubble in an infinitely large and eternally inflating multiverse. The space between bubbles continues to expand due to ongoing inflation, keeping the bubbles separated. The multiverse as a whole is expanding, or more accurately, inflating, with new space constantly being created between the bubble universes. This raises the question, what is the multiverse expanding into? The answer remains the same as for our universe: nothing. The multiverse, if it exists, is all of space-time. The inflationary expansion is intrinsic to the multiverse's geometry and does not require an external space. The multiverse hypothesis is speculative and controversial. It is difficult, or perhaps impossible, to test directly because we cannot observe other bubble universes. They are beyond our cosmic horizon, and the space between them is expanding so rapidly that signals from them cannot reach us. Some physicists embrace the multiverse as a natural consequence of inflation and as a potential explanation for the fine-tuning of physical constants in our universe. Others reject it as unscientific, arguing that a theory that cannot be tested is not a scientific theory at all. The multiverse also raises philosophical questions. If there are infinitely many universes with different properties, does our universe lose its uniqueness? Does the existence of other universes affect the meaning or value of our existence? These are questions that go beyond physics and touch on metaphysics and philosophy. They remind us that the deepest questions in cosmology are not just about mathematics and observations, but about our place in reality. Regardless of whether the multiverse exists, the concept of eternal inflation illustrates a key point about expansion. Even in a scenario with multiple universes, each expanding and inflating, there is no need for an external space. The multiverse, like our universe, is self-contained. Expansion is a property of space-time itself, driven by the energy content and described by the equations of general relativity. There is no outside. The mathematics of expansion, understanding the scale factor. While we've discussed cosmic expansion conceptually, it's worth exploring the mathematical framework that describes it, even at a basic level. This will help clarify what we mean when we say space itself is expanding, and why this expansion doesn't require an external space. In general relativity, the geometry of space-time is described by the metric, a mathematical object that tells us how to calculate distances and intervals between events. For a homogeneous and isotropic universe, the metric takes a specific form called the Friedmann-Lemaitre-Robertson-Walker metric, or FLRW metric for short. This metric includes a scale factor, usually denoted by the letter A, which changes with time. The scale factor tells us how distances in the universe change as time progresses. Imagine marking two galaxies with cosmic coordinates, fixed labels that don't change as the universe evolves. The actual physical distance between these galaxies is the coordinate distance multiplied by the scale factor. As the universe expands, the scale factor increases, and so does the physical distance, even though the coordinate distance remains constant. This is the mathematical way of expressing that space itself is expanding. The coordinates provide a reference frame, and the scale factor describes how that reference frame stretches over time. The evolution of the scale factor is governed by the Friedmann equations, derived from Einstein's field equations of general relativity. These equations relate the rate of change of the scale factor to the energy density and pressure of the matter and energy in the universe. The first Friedmann equation tells us how fast the universe is expanding at any given time, depending on its energy content and spatial curvature. The second equation describes how the expansion rate changes over time, whether it's accelerating or decelerating. One of the key insights from these equations is that the expansion rate depends on what's in the universe. Matter, which has positive energy density but negligible pressure, causes the expansion to decelerate. Radiation, which has both energy density and pressure, causes even stronger deceleration. But dark energy, with negative pressure, causes the expansion to accelerate. The current state of the universe, with its mix of matter, radiation, and dark energy, determines whether the expansion is speeding up or slowing down. The scale factor also helps us understand redshift, the stretching of light as it travels through expanding space. When light is emitted from a distant galaxy, it has a certain wavelength. As the light travels toward us, the space through which it's moving is expanding, and this expansion stretches the wavelength of the light. The amount of stretching is directly related to how much the scale factor has increased during the light's journey. By measuring the redshift of distant galaxies, astronomers can determine how much the universe has expanded since the light was emitted, and this allows them to reconstruct the expansion history of the universe. The mathematical description makes it clear that expansion is a property of the metric of the geometry of space-time itself. There is no reference to an external space or a boundary. The scale factor simply tells us how distances within the universe change over time. When we ask what the universe is expanding into, we're asking a question that doesn't fit within this mathematical framework. The framework describes everything intrinsically in terms of what's happening within the universe, without any need for an external reference. This might seem abstract, but it's important to understand that the mathematics of general relativity has been extraordinarily successful in describing the universe. The predictions of the Friedmann equations match observations with remarkable precision. The expansion rate, the relationship between distance and recession velocity, the evolution of the cosmic microwave background, the formation of large-scale structure, all of these are explained by the mathematical framework of expanding space-time. The fact that this framework works so well, without invoking any external space, is strong evidence that our understanding is correct. The horizon problem and how inflation solves it. We've mentioned cosmic inflation as a period of extremely rapid expansion in the early universe. But it's worth diving deeper into why inflation was proposed and how it solves some of the biggest puzzles in cosmology. Understanding inflation also helps clarify the nature of expansion and reinforces the idea that space can expand without expanding into anything. The horizon problem is one of the key puzzles that inflation addresses. When we look at the cosmic microwave background, we see that it has almost exactly the same temperature in all directions, to within about 1 part in 100,000. This uniformity is remarkable and suggests that different regions of the early universe were in thermal equilibrium, meaning they had time to exchange energy and reach the same temperature. But here's the problem. According to standard Big Bang cosmology, without inflation, regions on opposite sides of the sky were too far apart to have ever been in causal contact. Even traveling at the speed of light, the maximum speed at which information can propagate, there wasn't enough time for these regions to communicate and equalize their temperatures. This is called the horizon problem because each region has a particle horizon, the maximum distance from which light could have reached that region since the Big Bang. Regions beyond each other's horizons cannot have influenced each other, yet they have the same temperature. How can this be explained? Inflation solves this problem elegantly. The theory proposes that before the period described by standard Big Bang cosmology, there was a brief phase of exponential expansion during which the universe grew by an enormous factor in a tiny fraction of a second. During this inflationary phase, regions that are now on opposite sides of the observable universe were once much closer together close enough to be within each other's horizons. They had time to reach thermal equilibrium before inflation began. Then inflation rapidly expanded these regions to enormous distances, far beyond each other's current horizons, while preserving their initial uniformity. Think of it this way. Imagine you have a small patch of space where everything has reached the same temperature. Now inflate that patch to enormous size. The different parts of the expanded region will still have the same temperature, even though they're now so far apart that they can't communicate. This is what happened during cosmic inflation. The observable universe today was once a tiny, causally connected region that underwent exponential expansion, becoming much larger than the current observable universe. The inflationary expansion was incredibly fast, faster than the speed of light. This might seem to violate special relativity, but it doesn't. Special relativity prohibits objects from moving through space faster than light, but it places no limit on how fast space itself can expand. During inflation, galaxies or particles weren't moving through space faster than light. Rather, the space between them was expanding so rapidly that they were carried apart faster than light could travel between them. This is a crucial distinction and one that applies to cosmic expansion more generally. Objects don't move through space. Space itself changes. Inflation also explains the flatness of the universe. Before inflation, the universe could have had any amount of spatial curvature. But exponential expansion has the effect of smoothing out curvature, making space appear flat. It's like inflating a balloon to enormous size. The surface becomes so large that any local region appears flat, even though the overall shape might be curved. Observations indicate that our universe is very close to flat, and inflation provides a natural explanation for this. Another remarkable feature of inflation is that it predicts the existence of tiny quantum fluctuations that get blown up to cosmic scales. In the very early universe, space-time itself is subject to quantum uncertainty. There are random fluctuations in the energy density at the quantum level. Normally, these fluctuations are incredibly small and insignificant. But during inflation, they get stretched to macroscopic and even cosmic scales. These stretched fluctuations become the seeds for all the structure we see in the universe today. The galaxies, galaxy clusters, and the large-scale cosmic web. They also leave an imprint on the cosmic microwave background as tiny temperature variations. The predictions of inflation for the pattern and amplitude of these fluctuations match observations remarkably well, providing strong support for the theory. Inflation illustrates in a dramatic way that space can expand, and expand rapidly, without needing an external space to expand into. The inflationary expansion was intrinsic to space-time, driven by the energy of the inflaton field, and it transformed a tiny region into something vastly larger, all within the framework of general relativity. There was no outside, no pre-existing space that the inflating region was filling. The expansion was a change in the scale of space itself, redshift, and the stretching of space. One of the most important pieces of evidence for cosmic expansion is redshift, the phenomenon where light from distant galaxies is shifted toward longer wavelengths. Understanding redshift helps clarify what we mean by the expansion of space, and provides concrete, observable evidence that space itself is changing. When astronomers observe distant galaxies, they measure the spectrum of light coming from those galaxies. The spectrum contains bright and dark lines at specific wavelengths, corresponding to the emission and absorption of light by atoms. By comparing the observed wavelengths of these lines to the known wavelengths measured in a laboratory, astronomers can determine whether the light has been redshifted or blueshifted. For almost all distant galaxies, the light is redshifted, meaning the observed wavelengths are longer than they should be. The farther away a galaxy is, the the greater its redshift. There are different physical mechanisms that can cause redshift. The most familiar is the Doppler effect, where the motion of a source toward or away from an observer changes the frequency of waves. If a galaxy is moving away from us through space, the light it emits will be Doppler shifted to longer wavelengths. This is the explanation that's often given in popular accounts of cosmic expansion, and it's not entirely wrong, but it's not the whole story. In the context of an expanding universe, the primary cause of redshift is not the motion of galaxies through space, but the expansion of space itself. As light travels from a distant galaxy to us, the space through which the light is moving is expanding. This expansion stretches the wavelength of the light, increasing it in proportion to how much the universe has expanded during the light's journey. This is called cosmological redshift, and it's fundamentally different from Doppler redshift. To understand the difference, consider the scale factor of the universe, the quantity that describes how distances change over time. When light is emitted from a galaxy, the scale factor has a certain value. By the time the light reaches us, the scale factor has increased due to cosmic expansion. The ratio of the final scale factor to the initial scale factor tells us how much the universe has expanded during the light's journey, and this ratio is directly related to the redshift. If the universe has doubled in size, the wavelength of the light has also doubled, corresponding to a specific redshift value. This cosmological redshift is evidence that space itself is expanding. The light isn't being shifted because the galaxy is moving through space in the conventional sense. It's being shifted because the space through which the light is traveling is stretching. This stretching affects all wavelengths of light uniformly, which is why we can use redshift as a measure of cosmic expansion. The relationship between redshift and distance is given by Hubble's law, which states that the recession velocity of a galaxy is proportional to its distance. However, at large distances, this simple relationship breaks down because the expansion rate of the universe has changed over time. The universe's expansion was decelerating for most of its history due to the gravitational pull of matter, but it began accelerating about 6 billion years ago due to dark energy. To accurately relate redshift to distance for very distant galaxies, astronomers need to take into account the entire expansion history of the universe, including these changes in the expansion rate. Redshift also allows astronomers to look back in time. Light from a galaxy with a high redshift was emitted when the universe was much younger and smaller. By observing galaxies at different redshifts, astronomers can study how galaxies have evolved over cosmic time, how the rate of star formation has changed, and how the large-scale structure of the universe has developed. The most distant galaxies observed have redshifts greater than 10, meaning their light was emitted when the universe was less than 500 million years old, just a few % of its current age. The cosmic microwave background itself is highly redshifted. When the CMB photons were emitted about 380,000 years after the Big Bang, they had wavelengths corresponding to visible and ultraviolet light. But the universe has expanded by a factor of about 1,100 since then, stretching these wavelengths into the microwave part of the spectrum. The CMB we observe today is the redshifted remnant of that early light, cooled from thousands of degrees to just 2.7 degrees above absolute zero. Redshift is thus a direct observable consequence of cosmic expansion. It provides tangible evidence that space is stretching, carrying galaxies apart and stretching the light that travels between them. And crucially, this stretching of space does not require an external space for the universe to expand into. The redshift is a change in the wavelength of light within the universe caused by the changing scale factor of space-time, all described within the framework of general relativity. The role of dark matter in cosmic structure. While dark energy drives the accelerating expansion of the universe on the largest scales. Dark matter plays a crucial role in the formation and evolution of cosmic structures like galaxies and galaxy clusters. Understanding dark matter helps us see the full picture of how the universe has evolved from the smooth state shortly after the Big Bang to the rich tapestry of structures we observe today. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it invisible to telescopes. We know it exists because of its gravitational effects on visible matter, on the motion of stars and gas in galaxies, on the bending of light from distant sources, and on the large-scale structure of the universe. Dark matter makes up about 27% of the total energy density of the universe, compared to about 5% for ordinary matter, the stuff that makes up stars, planets, and us, and 68% for dark energy. The nature of dark matter remains one of the biggest mysteries in physics. We don't know what particles it's made of, though there are many candidates. The leading hypothesis is that dark matter consists of weakly interacting massive particles, or WIMPs, which interact with ordinary matter only through gravity and possibly the weak nuclear force. Other candidates include axions, sterile neutrinos, and primordial black holes. Despite extensive searches, dark matter particles have not yet been directly detected, though efforts continue with ever more sensitive experiments. What we do know is that dark matter played a crucial role in the formation of galaxies. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny variations in density. These variations, the seeds of structure, were imprinted during cosmic inflation as quantum fluctuations that got stretched to macroscopic scales. Without dark matter, these tiny variations would not have been able to grow into galaxies and galaxy clusters because the expansion of the universe would have dispersed them. Dark matter changes the picture because it interacts only gravitationally. Unlike ordinary matter, which can radiate energy and lose momentum through electromagnetic interactions, dark matter cannot cool down or clump easily. But its gravitational pull is strong enough to amplify the initial density variations. Regions with slightly more dark matter attracted more matter, both dark and ordinary, and gradually grew denser over time. These overdense regions eventually collapsed under their own gravity to form dark matter halos, gravitational wells within which ordinary matter could accumulate, cool, and form stars and galaxies. The distribution of dark matter determines the large-scale structure of the universe. Dark matter halos provide the scaffolding on which galaxies are built. Computer simulations of cosmic structure formation, which track the evolution of dark matter and ordinary matter from the early universe to the present, show that dark matter forms a cosmic web, a network of filaments and nodes where galaxies and galaxy clusters reside. The voids between these filaments are largely empty of both dark and ordinary matter. Observations of the distribution of galaxies match these simulations remarkably well, providing strong indirect evidence for dark matter. Within galaxies, dark matter dominates the mass. The visible stars and gas make up only a small fraction of the total mass. The rest is dark matter, distributed in a roughly spherical halo extending far beyond the visible disk of the galaxy. The gravitational pull of this dark matter halo affects the motion of stars and gas in the galaxy. And by measuring these motions, astronomers can infer the distribution and amount of dark matter. Dark matter also plays a role in cosmic expansion, though not in the way dark energy does. Dark matter, like ordinary matter, has positive energy density and negligible pressure, so its gravitational effect is to slow down the expansion. In the early universe, when matter dominated the energy density, the expansion was decelerating. But as the universe expanded and the density of matter decreased, dark energy, which has a constant energy density, eventually came to dominate, and the expansion began to accelerate. The interplay between matter, both dark and ordinary, and dark energy determines the expansion history and ultimate fate of the universe. Understanding dark matter is essential for a complete picture of the universe. While dark energy affects the expansion of space on the largest scales, dark matter affects the formation and evolution of structures within that expanding space. Together, they shape the universe we observe, from the cosmic microwave background to the distribution of galaxies, to the motions of stars within those galaxies. And like dark energy, dark matter operates entirely within the framework of general relativity, without requiring any external space or extra dimensions beyond the four of spacetime, gravitational waves, and the fabric of spacetime. One of the most dramatic confirmations of general relativity and the dynamic nature of spacetime came in 2015 with the first detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, or LIGO. Gravitational waves are ripples in the fabric of spacetime itself, produced by violent cosmic events like the collision of black holes or neutron stars. Their detection not only confirmed a major prediction of Einstein's theory, but also provided a new way to observe the universe and to understand the nature of space-time. Gravitational waves are fundamentally different from electromagnetic waves like light. Light is a disturbance in electromagnetic fields, propagating through space at the speed of light. Gravitational waves, on the other hand, are disturbances in space-time itself. When a gravitational wave passes through a region of space, it causes distances to oscillate, stretching space in one direction while compressing it in a perpendicular direction. This stretching and compressing is incredibly small. Even for the powerful waves detected by LIGO, the change in distance is only about 1/10,000th the diameter of a proton, but it's measurable with extraordinarily sensitive instruments. The existence of gravitational waves shows that space-time is not a fixed, rigid structure, but a dynamic entity that can vibrate and ripple. Just as cosmic expansion shows that space can stretch uniformly on large scales, gravitational waves show that space can oscillate locally in response to the motion of massive objects. Both phenomena illustrate that space-time has physical properties, that it can change and respond to energy and matter, and that it's an integral part of the universe, not just a passive background. Gravitational waves are produced whenever masses accelerate asymmetrically. In principle, any accelerating mass produces gravitational waves, but the effect is incredibly weak for ordinary objects. Only the most extreme cosmic events produce gravitational waves strong enough to be detected on Earth. The first gravitational waves detected by LIGO came from the merger of two black holes, each about 30 times the mass of the Sun, located over 1 billion light-years away. As the black holes spiraled toward each other, they emitted gravitational waves that carried away energy, causing them to spiral inward faster until they finally merged in a fraction of a second, releasing more energy in gravitational waves than all the stars in the observable universe combined emit as light. When these gravitational waves reached Earth, they caused the space between the mirrors in LIGO's detectors to oscillate by an incredibly tiny amount. But LIGO is sensitive enough to measure these minute changes, and the signal matched the predictions of general relativity with stunning precision. Since that first detection, LIGO and its partner detectors have observed dozens of gravitational wave events, including mergers of black holes, neutron stars, and mixed pairs. Each detection provides information about the masses, spins, and distances of the merging objects, and each confirms the predictions of general relativity in extreme conditions. Gravitational waves also provide a unique window on the universe because they travel through space-time largely unimpeded. Unlike light, which can be absorbed or scattered by dust, gas, and other matter, gravitational waves pass through almost everything without interaction. This means they can bring us information from regions of the universe that are invisible to telescopes, from the interiors of dense objects, from the moments just after the Big Bang, and from other events hidden from electromagnetic observations. There are ambitious plans to detect gravitational waves from the very early universe, potentially from the inflationary epoch itself. If inflation occurred, it should have produced a background of gravitational waves that might be detectable in the polarization pattern of the cosmic microwave background. Finding these primordial gravitational waves would be a major discovery, providing direct evidence for inflation and probing physics at extraordinarily high energies, far beyond what can be achieved in particle accelerators. Gravitational waves also have implications for our question about what the universe is expanding into. They demonstrate that space-time is not a fixed entity, but something dynamic and responsive. Just as space can expand uniformly on cosmic scales, it can also ripple and oscillate on smaller scales. These phenomena are intrinsic to space-time itself, described entirely within the framework of general relativity, without invoking any external space or extra dimensions. The fabric of space-time is the arena in which all physical phenomena occur, and it's an active participant in those phenomena, not just a passive container. The detection of gravitational waves has opened a new era in astronomy, one where we can observe the universe not just with light, but with ripples in space-time itself. This multi-messenger astronomy, combining electromagnetic observations with gravitational wave detections, is providing unprecedented insights into the most extreme and energetic events in the cosmos. And it's all possible because space-time is a physical entity that can carry information across the universe, stretching, compressing, and vibrating in response to the matter and energy within it. The anthropic principle and our place in the cosmos. As we explore the question of what the universe is expanding into, we inevitably confront questions about our place in the cosmos and why the universe has the properties it does. The anthropic principle addresses these questions by noting that the universe must have properties compatible with the existence of observers like us. This principle is both profound and controversial, and it relates to our understanding of cosmic expansion in interesting ways. The anthropic principle comes in different versions. The weak anthropic principle simply states that we observe the universe to have properties consistent with our existence because if it didn't have those properties, we wouldn't be here to observe it. This is almost tautological but still meaningful. For example, if the universe were not old enough for stars to have formed and produced heavy elements, there would be no planets or life. The fact that we exist places constraints on the properties of the universe we can observe. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop at some stage in its history. This version is more controversial because it seems to imply that the universe was designed or fine-tuned for life, which raises philosophical and theological questions that go beyond science. Many physicists are skeptical of the strong anthropic principle, preferring to look for physical explanations for the apparent fine-tuning of the universe's properties. The universe does appear to be fine-tuned for life in several respects. The strength of the fundamental forces, the masses of elementary particles, the density of dark energy, all of these parameters seem to be set with remarkable precision. If any of them were significantly different, stars wouldn't form, atoms wouldn't be stable, or the universe would have recollapsed or expanded so rapidly that structure couldn't form. The fact that these parameters have values compatible with the existence of complex structures, like galaxies, stars, planets, and life, is striking and demands explanation. One possible explanation is the multiverse. If inflation is correct and produces a vast number of bubble universes with different properties, then it's not surprising that we find ourselves in one of the universes where conditions are right for life. This is a selection effect. We can only observe a universe that allows observers to exist. In this view, our universe is not special or fine-tuned. It's simply one of countless universes, and we happen to inhabit one where the conditions are right for us. This explanation is elegant but untestable in the usual sense. We cannot observe other universes to verify that they exist or that they have different properties. Some physicists argue that the multiverse is therefore not a scientific hypothesis but a philosophical speculation. Others contend that if the multiverse arises naturally from a well-established theory like inflation, then it should be taken seriously, even if we cannot directly observe other universes. The anthropic principle also relates to cosmic expansion in another way. The rate of expansion, both in the past and present, affects the formation of structure and the evolution of life. If the early universe had expanded too rapidly, matter would have been too diffuse to form galaxies and stars. If it had expanded too slowly, the universe might have recollapsed before life could develop. The observed expansion rate is within the narrow range that allows for the formation of long-lived stars and the development of complex chemistry. Similarly, the accelerating expansion driven by dark energy affects the future of the universe and the longevity of life. If dark energy were much stronger, the expansion would have accelerated so rapidly that galaxies couldn't have formed in the first place. If it were much weaker or negative, the universe might recollapse. The observed value of dark energy, while mysterious, is consistent with a universe that can support life for billions of years. These observations don't prove that the universe was designed for life, but they do highlight the remarkable coincidences that make our existence possible. Whether these coincidences are explained by a multiverse, by some deeper principle we haven't discovered, or by design, remains an open question. What's clear is that our understanding of cosmic expansion is intimately tied to our understanding of the conditions necessary for life and our place in the cosmos. The question of what the universe is expanding into takes on a different character when viewed through the lens of the anthropic principle. If the universe is all that exists, if there is no outside, then we are not just observers within the universe, but part of it, products of its evolution. Our existence is evidence that the universe has the right properties to produce complexity and consciousness. Understanding cosmic expansion, understanding that it requires no external space, is part of understanding our own origins and place in reality. But just before we continue further into this mind-bending journey, I want to take a moment to thank the sponsor of today's video, Brilliant. Understanding concepts like cosmic expansion, space-time curvature, and general relativity requires developing a deep intuition for physics and mathematics, and that's exactly what Brilliant helps you do. Brilliant is a platform for learning STEM topics through interactive, hands-on problem solving. Whether you want to understand the math behind Einstein's equations, explore the principles of quantum mechanics, or dive into data science and computer programming, Brilliant has courses designed to build your skills from the ground up. Their approach is engaging and effective, breaking complex topics into manageable pieces and letting you learn by doing. I've personally used Brilliant to refresh my understanding of differential geometry, which is essential for general relativity, and I found the interactive approach far more effective than just reading a textbook. If you're curious about the universe and want to develop the tools to understand it deeply, I highly recommend checking out Brilliant. You can try everything Brilliant has to offer for free for a full 30 days by visiting brilliant.org/spacedust or clicking the link in the description. Plus, the first 200 people to sign up get 20% off an annual premium subscription. That's brilliant.org/spacedust. Now, let's get back to exploring the nature of cosmic expansion, the limits of language and imagination. One of the reasons the question, "What is the universe expanding into?" is so difficult to answer satisfactorily is that it bumps up against the limits of human language and imagination. Our language evolved to describe everyday experiences, objects moving through space, containers and contents, causes and effects. When we try to use this language to describe the universe as a whole, we run into problems. The universe is not an object in the usual sense, and its expansion is not motion in the usual sense. We lack the words and concepts to capture the reality fully. Consider the word into. It implies a direction, a destination, a space that is separate from the thing moving. When we say a car is driving into a garage, we mean that the car is moving through space, from outside the garage to inside it. The garage is a pre-existing space that the car enters. But the universe is not moving into anything because there is no pre-existing space separate from the universe. The expansion is not directional in the sense of moving towards something or into something. It is an increase in the scale of space itself, happening everywhere and in all directions simultaneously. Our intuition, shaped by experience, tells us that everything must have a boundary, an inside and an outside. A room has walls. A planet has a surface. Even the largest objects we can directly experience, like oceans or the atmosphere, have edges. But the universe, as far as we know, does not. If it's infinite, it has no boundary. If it's finite and closed, like the surface of a sphere, it has no boundary in the sense of an edge, though it has a finite extent. Our intuition fails us here because we have no direct experience with spaces that are finite but unbounded, or with spaces that are infinite and uniform. Imagination also has its limits. We can visualize 3 dimensions, more or less, and we can use mathematical tricks to represent higher dimensions. But truly imagining a 4-dimensional space-time, let alone the curved and expanding space-time of general relativity, is beyond our cognitive abilities. We rely on analogies like the balloon, on mathematical formalisms, and on carefully constructed thought experiments to grasp these concepts. But even then, there's a sense that we're only approximating the truth, capturing facets of it but not the whole. The philosopher Ludwig Wittgenstein famously said, "The limits of my language mean the limits of my world." In cosmology, we encounter the limits of language in a profound way. We're trying to describe a reality that is fundamentally alien to everyday experience, and our language is inadequate to the task. This doesn't mean we can't understand the universe. Mathematics provides a precise language that goes beyond ordinary words. But it does mean that when we try to communicate these ideas to each other, we must be aware that the words we use carry connotations and implications that may not apply. This is why physicists are often careful to say that the universe is not expanding into anything, rather than trying to describe what it is expanding into. The question itself may be based on a faulty premise, a misunderstanding of what expansion means in the context of general relativity. By rejecting the premise, by saying that expansion does not require an into, we acknowledge the limitations of our intuitive concepts and embrace a more accurate, if less intuitive, understanding of reality. This linguistic and conceptual challenge is not unique to cosmology. Quantum mechanics, with its wave-particle duality, entanglement, and uncertainty principles, also defies everyday intuition and language. The same is true for the extreme conditions near black holes, where space-time curvature becomes so intense that time and space exchange roles. In all these cases, we're pushing the boundaries of human understanding, exploring regimes where the rules of everyday experience no longer apply. The universe is under no obligation to be comprehensible to us. Yet remarkably, we have made enormous progress in understanding it through the power of mathematics, observation, and rigorous thinking. The role of general relativity in shaping our understanding. Throughout this discussion, we've repeatedly referred to general relativity as the framework for understanding cosmic expansion and the nature of space-time. It's worth pausing to appreciate just how revolutionary this theory is and how it fundamentally changed our view of the universe. Before general relativity, space and time were thought of as fixed and absolute, a stage on which the events of the universe unfold. Gravity was a force, a mysterious action at a distance that somehow caused objects to attract each other. Einstein's insight was that gravity is not a force, but a manifestation of the curvature of space-time. Mass and energy cause space-time to curve, and objects move along the straightest possible paths, geodesics, through this curved space-time. What we perceive as gravitational attraction is simply objects following the geometry of space-time. This reinterpretation of gravity as geometry had profound implications. It meant that space and time are not passive, but active, dynamic entities that interact with matter and energy. It opened the door to the possibility that space-time could have a beginning, an evolution, and potentially an end. It allowed for solutions to Einstein's equations describing expanding or contracting universes, black holes, gravitational waves, and other phenomena that would have been unimaginable in the Newtonian framework. General relativity is also a beautifully unified theory. It describes gravity and the large-scale structure of the universe with the same set of equations. The motion of a planet around a star, the bending of light by a massive object, the expansion of the universe, all are different manifestations of the same underlying principle, the curvature of space-time. This unification is a hallmark of progress in physics, bringing together seemingly disparate phenomena under a common framework. The theory has been tested to extraordinary precision. Observations of the orbit of Mercury, which deviates slightly from Newtonian predictions due to relativistic effects, provided an early confirmation. The bending of starlight by the Sun during a solar eclipse, observed in 1919, made Einstein famous. More recently, the detection of gravitational waves by LIGO in 2015, ripples in space-time caused by colliding black holes, confirmed another prediction of general relativity and opened a new window on the universe. The precession of orbits, the time dilation observed in GPS satellites, the imaging of the event horizons of black holes by the Event Horizon Telescope, all of these confirm the predictions of general relativity with stunning accuracy. Yet general relativity is not the final word. It is a classical theory, meaning it does not incorporate quantum mechanics, the theory that describes the behavior of particles at the smallest scales. At extremely high energies and small distances, such as those present at the moment of the Big Bang or inside black holes, both general relativity and quantum mechanics are needed, but they are not yet fully compatible. The search for a theory of quantum gravity, a unified framework that combines general relativity and quantum mechanics, is one of the greatest challenges in theoretical physics. Candidates include string theory, loop quantum gravity, and other approaches, but none has yet achieved the status of a well-confirmed theory. Despite this limitation, general relativity remains our best description of gravity and the large-scale structure of the universe. It is the foundation on which modern cosmology is built, and it is the framework within which we understand cosmic expansion. The question of what the universe is expanding into is answered or dissolved by general relativity. The theory shows that expansion is an intrinsic property of space-time, not motion into an external space. Philosophical implications and the nature of existence. The question of what the universe is expanding into is not just a scientific question, it's also a philosophical one. It touches on deep issues about the nature of existence, the meaning of the universe, and our place within it. One philosophical issue is the concept of nothing. When we say the universe is not expanding into anything, we are invoking the idea of nothing. But what does that mean? Is nothing simply the absence of something, or is it a kind of thing in itself? Philosophers have debated the nature of nothingness for millennia. In the context of the universe, nothing means the absence of space, time, matter, and energy. It is not a void or an empty space, because even a void is a kind of space. It is literally no thing, the complete absence of existence. This is hard to wrap one's mind around. We're used to thinking of empty space as a kind of container, a place where things could be but aren't. But space itself is a physical entity, described by the metric in general relativity. And if there's no space, there's no place, no where, no when. The universe, in this view, is not a thing within space, but is all of space, and there is no outside to speak of. This challenges our intuitive notions of existence and forces us to think more carefully about what we mean by reality. Another philosophical issue is the contingency of the universe. If the universe is all that exists, if there is no outside or external framework, then the universe is, in a sense, self-contained and self-explanatory. It does not depend on anything else for its existence. This raises questions about causation and explanation. Why does the universe exist? Why is it the way it is? These are questions that physics alone may not be able to answer. Some physicists and philosophers argue that the universe could be a brute fact, something that exists without a deeper explanation. Others seek explanations in the multiverse, in fundamental theories like string theory, or in metaphysical or theological frameworks. The idea that the universe could be infinite also has philosophical implications. An infinite universe means that everything that can happen does happen somewhere. If space goes on forever and is filled with matter distributed randomly on large scales, then there are infinitely many regions that look like our own, including regions with planets identical to Earth and people identical to you and me. This is deeply strange and challenges our sense of uniqueness and identity. It also raises questions about probability and explanation. In an infinite universe, even extremely unlikely events occur infinitely many times. Does this make them less special or less in need of explanation? The concept of the multiverse, if true, amplifies these philosophical puzzles. If there are infinitely many universes, each with different properties, then our universe loses its uniqueness. The fine-tuning of physical constants, which seems to require explanation, might simply be a selection effect. We exist in a universe with the right properties for life because only such universes can contain observers like us. This is the anthropic principle, and it is controversial. Some see it as a profound insight, while others see it as a cop-out, an admission of defeat in the search for deeper explanations. These philosophical questions remind us that science and philosophy are deeply intertwined. While science provides the tools to investigate the universe empirically, philosophy helps us interpret the results, understand their implications, and grapple with the questions that science cannot yet answer. The question of what the universe is expanding into sits at the boundary between science and philosophy, a place where empirical knowledge meets conceptual analysis and where the limits of our understanding become most apparent. The cosmological principle and the uniformity of space. One of the key assumptions in modern cosmology is the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. Homogeneous means that the universe looks the same at every location, and isotropic means that it looks the same in every direction. This principle simplifies the equations of general relativity and allows cosmologists to construct models of the universe's evolution. The cosmological principle is well supported by observations. The cosmic microwave background, the afterglow of the Big Bang, is extraordinarily uniform across the sky, with temperature variations of only about 1 part in 100,000. The distribution of galaxies on the largest scales is also consistent with homogeneity and isotropy. While there are structures like galaxy clusters, superclusters, and cosmic voids, when averaged over distances of hundreds of millions of light years or more, the universe appears smooth and uniform. This uniformity has important implications for cosmic expansion. If the universe is homogeneous and isotropic, then the expansion must be the same everywhere. There is no special location or direction. Every observer, no matter where they are located, sees the same pattern of expansion. Galaxies receding with velocities proportional to their distances. This is consistent with the idea that space itself is expanding uniformly rather than objects moving through space from some central point. The cosmological principle also implies that there is no center or edge to the universe. In a homogeneous and isotropic universe, every point is equivalent. No location can claim to be the center of the expansion, and no direction can be said to point toward an edge. This is a powerful constraint on models of the universe and reinforces the idea that the universe is not expanding into an external space, but is expanding uniformly within its own geometry. However, the cosmological principle is an assumption, not a proven fact. It is possible that the universe is not perfectly homogeneous and isotropic, that there are large-scale variations in density or expansion rate that we have not yet detected. Some observations, such as the so-called dipole in the cosmic microwave background, a slightly higher temperature in one direction and lower in the opposite direction, suggest that the Earth, or more accurately the solar system, is moving relative to the rest frame defined by the CMB. This motion, about 370 kilometers per second, is consistent with the gravitational pull of nearby galaxy clusters and does not violate the cosmological principle. But other observations, such as the axis of evil, a mysterious alignment in the CMB fluctuations, have raised questions about whether the universe is truly isotropic on the largest scales. If the cosmological principle holds, then the universe's expansion is uniform and intrinsic, not requiring an external space. If the principle is violated on very large scales, then the universe might be more complex, with regions expanding at different rates or in different directions. This would not necessarily require an external space, but it would complicate the picture and raise new questions about the overall geometry and dynamics of the universe. Common misconceptions about cosmic expansion. Given the complexity and counterintuitive nature of cosmic expansion, it's no surprise that there are many common misconceptions. Addressing these misconceptions can help clarify what expansion really means and why the universe does not expand into anything. One misconception is that the Big Bang was an explosion at a point in space, with matter flying outward from that point. This is not correct. The Big Bang was not an explosion in space, but an expansion of space itself. Every point in the universe was part of the initial state, and the expansion began everywhere at once. There is no center of the Big Bang in space. If you could somehow rewind time and watch the universe contract, you would not see everything converging on a single point in space. Instead, you would see the density increasing everywhere, with all of space shrinking down to a singularity. Another misconception is that galaxies are moving through space away from us. While it's true that distant galaxies have high recession velocities, these velocities are not due to motion through space in the usual sense. The galaxies are not flying through space. Rather, the space between us and them is expanding, carrying them away. This distinction is more than semantic. Motion through space is limited by the speed of light, but the expansion of space is not. Distant galaxies can recede from us faster than the speed of light because the space between us is expanding rapidly. This does not violate relativity because they are not moving through space faster than light. The space itself is expanding. A related misconception is that expansion affects everything, including atoms, planets, and galaxies. This is not true. Expansion affects the space between unbound objects, like galaxies that are not gravitationally bound to each other. But within gravitationally bound systems, like atoms, planets, solar systems, and even galaxy clusters, the forces holding these systems together are much stronger than the effects of cosmic expansion. The expansion of space does not pull apart atoms or stretch planets. It only increases the distances between objects that are not held together by other forces. Another misconception is that there must be an edge to the universe, a boundary beyond which there is nothing. This intuition is strong because every object we encounter in everyday life has boundaries. But the universe, as a whole, does not necessarily have an edge. If the universe is infinite, it extends forever in all directions with no boundary. If it is finite and closed, like the surface of a sphere, it has a finite volume but no edge. You could travel in any direction and never reach a boundary, just as you can travel around the Earth's surface without reaching an edge. Some people also confuse the observable universe with the entire universe. The observable universe has a boundary, defined by the distance light has had time to travel since the Big Bang. But this is not an edge of the universe itself. It's simply the limit of what we can see. Beyond this horizon, the universe continues, possibly forever. The boundary of the observable universe is centered on us, but an observer in a distant galaxy would have their own observable universe centered on them with a different horizon. Finally, there is the misconception that science can tell us what the universe is expanding into, and if scientists say it's not expanding into anything, they must be wrong or hiding something. This misconception stems from a misunderstanding of what science can and cannot address. Science describes how the universe works, using observations, experiments, and mathematical models. General relativity, the best theory we have for describing the universe's large-scale structure, shows that expansion does not require an external space. This is not a limitation or a failure of science. It's a deep insight into the nature of reality. The universe is not expanding into anything because expansion is an intrinsic property of space-time itself, the ultimate fate of the universe. Understanding cosmic expansion also leads naturally to questions about the future. If the universe is expanding now, what will happen in the distant future? Will expansion continue forever, or will it eventually stop or reverse? The answer depends on the energy content of the universe, particularly the nature of dark energy. Current observations indicate that the universe is not only expanding, but accelerating, driven by dark energy. If this acceleration continues, the universe will expand forever, growing ever larger and colder. The ultimate fate of such a universe is sometimes called the Big Freeze or heat death. Over trillions of years, stars will exhaust their nuclear fuel and die. Galaxies will collide and merge, but eventually, the accelerating expansion will carry most galaxies beyond the cosmic horizon, making them forever unobservable and unreachable. The universe will become increasingly cold, dark, and empty. On even longer timescales, structures will decay. Planets will be ejected from their orbits or fall into remnant stars. Black holes will evaporate through Hawking radiation, a process that takes an unimaginably long time, on the order of 10 to the power of 100 years or more for the largest black holes. Eventually, the universe will reach a state of maximum entropy, where no structure or order remains, only a diffuse sea of particles and radiation at a temperature close to absolute zero. This is the heat death, a universe that has reached thermodynamic equilibrium with no energy available to do work. Another possible fate, if dark energy behaves differently than a cosmological constant, is the Big Rip. In this scenario, dark energy increases over time, causing the expansion to accelerate ever more rapidly. Eventually, the expansion becomes so violent that it tears apart galaxies, solar systems, planets, atoms, and even subatomic particles. The universe ends in a catastrophic disintegration of all structures. Current observations do not favor this scenario, but it remains a possibility depending on the exact nature of dark energy. If dark energy were to weaken or reverse, or if the universe were closed with enough mass to overcome dark energy, the expansion could eventually halt and reverse, leading to a big crunch. In this scenario, the universe would contract, becoming denser and hotter, eventually collapsing back to a singularity similar to the Big Bang. This would be the opposite of the current expansion, a universe that not only stops expanding, but contracts back in on itself. Some speculative theories propose that a big crunch could be followed by a new Big Bang, creating a cyclic or oscillating universe that expands and contracts repeatedly. However, current observations of accelerating expansion make the Big Crunch unlikely. The fate of the universe has implications for the question of what it is expanding into. If the universe expands forever, growing without limit, does it eventually fill some pre-existing infinite space? No, because there is no pre-existing space. The expansion creates new space, or more accurately, the scale of existing space increases. If the universe contracts in a big crunch, does it retreat from the space it occupied? Again, no. The contraction is a decrease in the scale of space itself, not a retreat into or out of something external. These scenarios remind us that the universe is not static but dynamic, evolving over vast stretches of time. The expansion we observe today is just one phase in a cosmic history that began with the Big Bang and will continue for trillions upon trillions of years, if not forever. Understanding this history and the forces that drive it is one of the great achievements of modern science, and it provides profound insights into the nature of existence itself, the limitations of our current understanding. Despite the remarkable progress in cosmology over the past century, there is much we still do not understand about the universe and its expansion. Recognizing these limitations is important for maintaining intellectual humility and for guiding future research. One major limitation is our understanding of dark energy. We know it exists because we observe its effects on the expansion rate, but we do not know what it is. Is it a cosmological constant, a property of space itself that remains constant over time? Or is it a dynamic field, something that changes and evolves, like the inflaton field thought to drive inflation? Different models of dark energy make different predictions for the future evolution of the universe and for the behavior of cosmic expansion at different epochs. Determining the nature of dark energy is one of the top priorities in cosmology and will require more precise observations and new theoretical insights. Another limitation is our understanding of the initial conditions of the universe. Why did the universe begin in the state it did, hot, dense, and uniform? What caused the Big Bang? These are questions that current physics cannot fully answer. Inflation provides a mechanism for generating the observed uniformity and structure, but it does not explain what caused inflation or what, if anything, came before it. Some theories propose that the Big Bang was not the beginning but a transition from a previous state, perhaps a contracting universe, or a fluctuation in a pre-existing space. Others suggest that time itself began with the Big Bang, making the question of what came before meaningless. We do not yet know which, if any, of these ideas is correct. We also lack a complete theory of quantum gravity, a unified framework that combines general relativity and quantum mechanics. At the extreme energies and small scales present at the moment of the Big Bang, or inside black holes, both theories are needed, but they give inconsistent answers. Quantum mechanics says that space and time are continuous and deterministic at large scales, but granular and probabilistic at small scales. General relativity treats space-time as a smooth, continuous manifold. Reconciling these views is a major unsolved problem in theoretical physics. A theory of quantum gravity might reveal new insights into the nature of space, time, and the expansion of the universe. The nature of space itself is still mysterious. Is space fundamentally continuous? Or is it made up of discrete units, like pixels on a screen? Is it emergent, arising from more fundamental entities or processes? These are questions at the cutting edge of theoretical physics, explored in approaches like string theory, loop quantum gravity, and other candidate theories of quantum gravity. If space is emergent or quantized, it could have implications for cosmic expansion and for the question of what the universe is expanding into. Finally, we are limited by the observational horizon. We can only observe the part of the universe from which light has had time to reach us. Regions beyond this horizon are inaccessible, at least with electromagnetic radiation. This means there could be large-scale structures or features of the universe that we cannot see and that could change our understanding of the cosmos. The universe beyond the horizon might be fundamentally different, or it might be more of the same. We cannot know for certain without observations, and such observations may never be possible. These limitations do not diminish the achievements of cosmology, but rather highlight the exciting challenges that remain. Each unanswered question is an opportunity for discovery, a chance to deepen our understanding of the universe and our place within it. Bringing it all together, a final answer. So, after this long journey through the history, theory, and implications of cosmic expansion, we return to the original question: what is the universe expanding into? The answer, as we've seen, is both simple and profound. The universe is not expanding into anything. There is no external space, no pre-existing void or arena that the universe is filling. The expansion is intrinsic to space itself, a change in the scale of distances within the universe, not motion into something outside the universe. This answer is grounded in general relativity, which describes space-time as a dynamic entity that can curve, stretch, and evolve. In this framework, space is not a fixed stage, but an active participant in the cosmic drama. The universe is all of space-time, everything that exists, and there is no outside to expand into. When we say the universe is expanding, we mean that the distances between galaxies and between all unbound objects are increasing over time. This increase is due to the stretching of space itself, driven by the energy content of the universe as described by Einstein's equations. The expansion does not have a center or an edge. It is uniform on large scales, consistent with the cosmological principle. Every observer, no matter where they are located, sees the same pattern of expansion, with distant galaxies receding in all directions. This is not because we are at the center, but because every point in the universe is equivalent. There is no special location, no privileged frame of reference. The universe may be infinite, extending forever in all directions, or it may be finite but unbounded, like the surface of a sphere. In either case, it does not have an edge or boundary into which it could expand. If it is infinite, it was always infinite, and the expansion is a change in the scale of structures within the infinite space. If it is finite, the expansion is an increase in the total volume, but this volume is intrinsic to the universe's geometry, not contained within some larger space. The Big Bang was not an explosion at a point, but an expansion of all of space, beginning everywhere at once. The observable universe is just the part of the universe we can see, limited by the finite age of the universe and the finite speed of light. The entire universe is likely much larger, possibly infinite, and it extends far beyond what we can observe. The expansion is accelerating due to dark energy, a mysterious form of energy that makes up most of the universe's energy density. This acceleration means the universe will likely expand forever, growing ever larger and colder, eventually reaching a state of maximum entropy. The ultimate fate of the universe is a big freeze, a cold, dark, empty cosmos, where no structure or activity remains. These findings are based on observations and on our best theories, particularly general relativity. While there is much we do not yet understand, including the nature of dark energy and the quantum nature of space-time, the framework of general relativity has been extraordinarily successful in describing the universe's large-scale structure and evolution. It provides a coherent, mathematically rigorous answer to the question of what the universe is expanding into. Nothing, because expansion is a property of space itself, not motion into an external space. This answer may not satisfy our intuitions, which are shaped by everyday experiences of objects expanding into surrounding space. But the universe is under no obligation to conform to our intuitions. Reality, especially at cosmic scales, is stranger and more wonderful than our common sense suggests. The challenge is to let go of our preconceptions and embrace the deeper understanding that science provides.